All right, let's summarize what we've learned so far. When something rotates or rolls, it also travels a certain distance. So it rotates a certain amount of radians and it travels a certain distance. The distance that it travels would be called the d, the displacement, 6 meters. So we're going to connect rotational variables to linear variables like linear kinematics variables like distance, velocity, and acceleration. First of all, this could be a little bit better. There's alpha. Alpha is the rotational acceleration. How quickly does the rotational velocity change? Well, rotational acceleration equals the linear acceleration divided by r. This w is omega, but it means rotational velocity, which equals the linear velocity divided by r. What does that mean? Something has a certain linear speed at which it rotates. How do you find the speed at which it rotates? Take the linear velocity, the distance over time that it moves, the regular velocity we've been talking about all year, divided by r, and you'll get the rotational velocity in radians per second. And finally, the radians. How do you get the radians? Take the distance something travels divided by the radius of the circular object that's actually rolling that distance. So that's how you connect the two. Now, we have linear kinematics equations. You should recognize all of these, but they have there what's called rotational analogs. How do you find the rotational acceleration? Well, it's the change in rotational velocity divided by the change in time. This is called the analog. If you look at the equation on the left, the linear equation you're used to, looks like the equation on the right, but this applies to rotation. We can also find the linear analog of this. The final rotational velocity equals the initial rotation velocity of an object times alpha, rotational acceleration times t, really delta t. So the average rotational velocity is equal to the change in the radians per unit time. Take this one over here, this VF squared, it becomes WF squared. The final rotational velocity squared equals the initial rotational velocity squared plus 2 alpha, rotational acceleration times delta theta. This is delta. How many radians has something traveled? It equals the initial rotational velocity times the time plus 1/2 alpha, the rotational acceleration times t squared. So these are the analogs, the rotational analogs. Let's take a look at this first problem. A ball with a radius of this starts from rest and accelerates 10 meters, that's d, and it starts from rest vi, and it goes to this velocity. What is the angular velocity? So they've given me all this linear information and they want angular velocity. Now, strategy 1 is to convert all to omega f, theta, theta, on and on. The second strategy is the smarter one. Solve the linear equation and then convert. That's a smarter way to do it. It's only one conversion versus 4, whatever. What do I mean? Well, we know VI equals 0, and we're told that the distance it travels is 10 meters, and we're told that the final linear velocity is 8.0 meters per second. And what's the acceleration? So I'm going to treat this as a linear problem, find the equation that fits. Only one equation on my reference table fits. Even though I want to find the angular acceleration, I treat it like a linear problem, and you get 64. Oops, this is squared. 64 equals 0 squared plus 2 times a times 10 meters. And so you get an acceleration of 3.2 meters per second squared. And then you say the rotational acceleration equals the linear divided by r, which is 3.2 meters per second squared, divided by our radius that we got above there, 0.10 meters, with two significant digits, 32 radians per second squared. So be smart. Don't do a whole lot of conversions. If they've got everything in linear, solve for the linear and then convert at the end. That's the moral of the story. Let's see. And that's it for that. So we'll stop there.